Welcome to the course on an introduction to information theory. So in this lecture we are going to talk about rate distortion theory. Now when we try to represent an arbitrary real number, to represent it losslessly, we would require infinite number of bits. Now whenever we try to represent it using finite number of bits, we are introducing distortion. So how do we know that our representation of this real number is good? So for that we need to introduce this notion of distortion measure. So in rate distortion theory, we are going to ask questions like, for example, if we specify that we can tolerate this much average distortion, then what is the minimum number of bits required to represent a source? Or let us say if I specify my rate, then what is the minimum distortion that I can achieve? So we will start off this discussion on rate distortion theory with a brief introduction and few definitions. I will define what is a rate distortion code and what do we mean by a rate distortion code is achievable, and then we will calculate rate distortion function for some simple examples like Bernoulli source with Hamming distortion measure, Gaussian source with squared error distortion measure, and we are going to talk about the description of independent Gaussian random variables, but they are not necessarily identically distributed. So a distortion measure is a measure of distance between the random variable and its representation. As I said, any real number, when we are an arbitrary real number, when you are trying to represent using fixed number of bits, we are introducing some sort of a distortion. So distortion measure is a measure of distance between this random variable and its representation. Now this measure of distance we will specify. There could be different ways in which we could define this measure of distance between the source alphabet and the reproduced alphabet. So a distortion measure is a mapping of set of source alphabet and reproduction alphabet pairs into a set of non-negative real number, and this set of non-negative real number will specify how much this source alphabet is differing from this reproduced alphabet. We say a distortion measure is bounded if the maximum value of distortion is finite. So if we define the maximum value of distortion as maximum value of distance between the random variable and its representation. Now if this is bounded, then we say the distortion measure is bounded. Now let us give some example of common distortion function. Hamming distortion function. So Hamming distortion measure is defined as follows. So when the source alphabet and the reproduced alphabet, when they are same, there is no distortion. So that is, distortion is 0 when the source alphabet and the reproduced alphabet is same. However, if they are different, then the distortion is 1. So in Hamming distortion, it is 0 if there is no error, and it is 1 if the bits are, if the source alphabet and the reproduced alphabet, they are different. Similarly, we could define squared error distortion. So squared error distortion is basically the Euclidean distance between the source alphabet and this reproduced alphabet. So, this is our squared error distortion function. Now, the distortion measure that we have defined so far is on symbol by symbol basis. Now, we could extend this definition for sequences as well. So, if you want to extend this definition of distortion measure for sequences, so this is a source sequence and this is a reproduced sequence, then the distortion measure can be written as average distortion measure per symbol. So, this is distortion between source symbol xi and the reproduced symbol xi hat. We sum over all n symbols and then we average it out. So, that is how we would define distortion measure for sequences. Now, as I said in the beginning of this lecture, in this rate distortion theory, given a source distribution and a distortion measure, we are interested in what is the minimum expected distortion for an available particular achievable particular rate. So, given a source distribution and given a distortion measure, what is the minimum expected distortion that is achievable for a particular rate? We can ask this question in a different way also. Given a source distribution and a distortion measure and given an average distortion criteria, we are interested in knowing what is the minimum rate that can be achievable. So, 2 raised to power nr n rate distortion code consists of following encoding function. So, this is your source sequence of n bit, this you are mapping to one of these rate distortion codes, and at the decoder, which is denoted by this function g of n, given that you have received one of these indices, you are interested in getting back an estimate of the sequence. Now, distortion for a rate distortion code is defined like this. So, this is the distortion measure between the source sequence and this is the reproduced sequence. I can also write this as xn hat. So, this is basically the average distortion between x of n and x hat of n. We say a rate distortion pair denoted by this rate r and this distortion d is said to be achievable if there exists a 2 raised to power nr n rate distortion code with following encoding and decoding function with as n tends to infinity, the expected distortion is less than equal to the given distortion d. Now, we could similarly define a rate distortion region. So, a rate distortion region for a source is the closure of set of all achievable rate distortion pair. That is our rate distortion region. And we define a rate distortion function as the infimum of all rates such that this rate distortion pair is in the rate distortion region of the source for a given distortion. Similarly, we can also define distortion rate function. This distortion rate function is defined as the infimum of all distortions d such that this pair rate and distortion is in the rate distortion region of the source for a given rate r. Now we define information rate distortion function for a source x with distortion measure given by d of x and x hat. We define information rate distortion as minimum mutual information between the source alphabet x and this reproduced alphabet x hat. So this is a source and this is a reproduced source. So mutual information between x and x hat, minimum of that, and minimization is taken over all conditional distribution p of x hat given x, for which the joint distribution p of x hat satisfies the expected distortion constraint. So for this information rate distortion function, we minimize this mutual information between x and x hat, and this minimization is over all conditional distribution of p x hat given x, such that over this joint distribution p of x hat, this expected distortion constraint is satisfied. Now this rate distortion function is also our information rate distortion function is also our rate distortion function. So rate distortion function for an IID source with distribution p of x and bounded distortion function given by d of x hat is equal to its associated information rate distortion function. In other words, the rate distortion function can be found by minimizing the mutual information between x and x hat, and we do this minimization over all conditional distribution of p of x hat given x, such that this joint distribution p of x hat satisfies the expected distortion constraint. And this rate distortion function is given by this, and this is the minimum achievable rate for a distortion t. Now let us illustrate, or let us compute this rate distortion function. So we will first take an example of a Gaussian source. So we have a Gaussian source x denoted by x, 0 mean, variance, sigma square. Now according to the definition, the rate distortion function is given by minimizing the mutual information between x and x hat, and this minimization is over all conditional distribution of f x hat given x, such that the expected distortion constraint is satisfied. Now let us compute the mutual information between x and x hat. So way we are going to compute this rate distortion function is as follows. We are going to lower bound this mutual information between x and x hat, and then we are going to show that this lower bound is achievable, and that is how basically we are going to show that that is the value of the rate distortion function. So mutual information between x and x hat, this is given by differential entropy of x minus differential entropy of x given x hat. Now x is a Gaussian source, 0 mean, variance, sigma square. So its differential entropy is given by this expression, half log of 2 pi e into sigma square. Now we know that translation does not change differential entropy. So differential entropy of x given x hat is same as differential entropy of x minus x hat given x hat. Now this is differential entropy of x minus x hat conditioned on x hat. So, we know that conditioning cannot increase entropy. So, h of x minus x hat is going to be greater than h of x minus x hat given x hat. So, in this step we are subtracting a larger quantity, and that is why I have here lower bound. Now, we know that given a second order moment, we know that Gaussian source has the maximum differential entropy, and that is why this is upper bounded by differential entropy of a Gaussian source with mean 0 and same variance, which is given by expected value of x minus x hat square. So, this greater than or equal to comes because differential entropy of h x minus x hat is upper bounded by differential entropy of a Gaussian random variable with same second order moment. Now, this is same as this, and we know what is the differential entropy of a Gaussian source. So, that is given by half log 2 pi e variance is expected value of x minus x hat whole square, that is this term. And what is this term? This is upper bounded by d. So, then we can write mutual information between x and x hat to be half log of 2 pi e times sigma square minus half log 2 pi e times d. That is because expected value of x minus x square is upper bounded by d. And then combining these terms, we get this. So, the mutual information between x and x hat is lower bounded by half log of sigma square by 2 by d. Now, we are going to show that this is actually achievable. This lower bound is achievable. So, if d is less than sigma square, we choose x to be x hat plus z. And what is x hat? X hat is given by is Gaussian distributed with 0 mean and variance sigma square minus d. What is z? Z is Gaussian distributed with 0 mean and variance d, and x is Gaussian distributed with mean 0 and variance sigma square. So, what is mutual information between x and x hat? This is given by differential entropy of x minus differential entropy of x given x hat. Now, x is Gaussian distributed, x given x hat is also Gaussian distributed, and we can compute this mutual information comes out to be half of log sigma square by t, and this is precisely the lower bound that we computed here. So, what we have shown is this mutual information is actually achievable if we take our x hat and z in this particular way. And what happens if d is greater than sigma square? In that case, we choose x equal to 0 with probability 1, and that gives us rate as 0. Now, as we said, this rate can also be written in terms of distortion. So, this rate I can also write in terms of distortion. So, I have this sigma square by d, or log of sigma square by d is 2r, or I can write sigma square by d to be 2 raised to the power 2r, or d is sigma square 2 raised to the power minus 2r. So, I can write distortion in terms of rate, and you can see if rate increases, then distortion decreases, and that makes sense. If we are using more number of bits to represent a quantity, basically our distortion is going to decrease. Now, let us take another example. This time we are considering a Bernoulli source, and we are considering Hamming distortion measure. So, we can show that the rate distortion function for this Bernoulli source is given by this expression. So, as long as d is within 0 and minimum of p and 1 minus p, it is given by h of p minus h of d, otherwise it is given by 0. Now, without loss of generality, let us assume that this p is less than half. Now, we are considering a Bernoulli source. This is a binary source. So, x XOR x hat. When x XOR x hat is 1, it means x is not same as x hat. That's so, when x is from Bernoulli source, x XOR x hat equal to 1 is equivalent of saying x is not same as x hat. Now, again here, to compute the rate distortion function, we will first put a lower bound on mutual information between x and x hat, and then we will show that this lower bound is achievable. So, let us compute this mutual information between x and x hat. Now, from the definition of mutual information, I can write this as h of x minus h of x given x hat. Now, what is x? X is a Bernoulli source with probability b. So, this is basically a binary source. Its entropy is given by h of p. This is binary entropy function of p. Now, what is the uncertainty in x given x hat? So, there is uncertainty in x only when it is not same as x hat. So, it's equivalent of, so uncertainty in x given x hat is basically uncertainty in x not equal to x hat, and that is given by this x XOR x hat. So, we can write this mutual information between x and x hat as h of p minus h of x XOR x hat given x hat. Now, again this is condition on x hat. If we remove this conditioning, we know that conditioning cannot increase entropy. So, this quantity is larger, h of x XOR x hat, this is more than x. So, we are subtracting a larger quantity, and that is why I have here mutual information between x and x hat is greater than equal to h of p minus h of x XOR x hat, and x XOR x hat is basically when there is error, and this probability of error is upper bounded by d. So, this is upper bounded. So, I can write this as greater than or equal to h of p minus h of d. So, the rate distortion function is given by this for the case when d is within minimum of p or 1 minus p. Now, let us consider the case when d lies between 0 to p. Now, remember, our objective is to cook up a distribution such that this rate is achievable with equality. So, we want, so x is distributed as Bernoulli with p, and we want h of x given x hat to be basically h of d. So, we have to cook up a distribution. So, we create a test channel. So, this is my x and this is my x hat. Now, I want to ensure, I want to create a joint distribution such that my x is distributed as Bernoulli, we know, with 0 probability 1 minus p, 1 with probability p, and I need to find out this distribution on x hat. Keeping in mind, we want to keep the distortion less than or equal to d. Now, we choose a distribution of x hat at the input of this test channel such that the output distribution is the specified distribution. So, let r is equal to probability of x hat being 1. So, we need to choose r in such a way such that r times 1 minus d plus 1 minus r times d, that is equal to p. If you go back here, r times, if this is a probability of x hat being 1. So, r times 1 minus d plus 1 minus r times d, that has to be p. So, if I do that, I get this input distribution on x hat. So, probability of x hat being 1, I get this as p minus d divided by 1 minus 2 times d. Now, if d is p lies between d and half, then probability of x hat being 1 is greater than or equal to 0 and probability of x hat being 0 is greater than or equal to 0. Then in this case, what we will see is this mutual information between x and x hat is equal to h of p minus h of d, where the expected distortion is given by d. So, if we take this input distribution on x hat, we are able to achieve this lower bound. So, then the rate distortion function is given by h p minus h of d. Now, for the case when d is greater than equal to p, r d is 0, and this we let x hat is equal to 0 with probability 1, and in this case mutual information between x and x hat comes out to be 0 and distortion is basically p. And similarly, for d greater than or equal to 1 minus p, we can achieve r d equal to 0 by setting x hat is equal to 1 with probability 1. In this case also, this mutual information between x and x hat will come out to be 0. Now, let us consider a source now. Now, this source is uniformly distributed. So, we have a source which is uniformly distributed in the set 1, 2, 3 and m. And let us compute its rate distortion function for Hamming distortion. And what is Hamming distortion again? So, if x is equal to x hat, this is 0, and if x is not equal to x hat, distortion is 1. Now consider any joint distribution that satisfies this distortion constraint of D. Now since D is probability of x not being equal to x hat, we can invoke Fano's lemma, and if we invoke Fano's lemma, we can show the uncertainty in x given x hat is less than equal to h of p probability of error, which is h of d plus d times log of m minus 1. This is p log of number of possibilities minus 1. So that is our Fano's lemma. So from Fano's lemma we get this. Next, we compute the mutual information between x and x hat. This is given by entropy of x minus entropy of x given x hat. Now from the Fano's lemma we have a upper bound on h of x given x hat. So if we subtract this upper bound, so since we are subtracting a larger quantity, we now have a lower bound on mutual information between x and x hat. So mutual information between x and x hat is lower bounded by log of m minus h of d minus d log of m. And of course this is maximum when, because x is uniformly distributed, so h of x will be log of m. Now we can achieve this lower bound by choosing our p of x hat to be uniformly distributed, and if we choose our conditional distribution in this way, that if x is equal to x hat, probability of x hat given x is 1 minus d, otherwise it is d by m minus 1. Now this bound is satisfied with equality when d is less than equal to 1 minus 1 by m. So the rate distortion function is given by, for this uniform source, is given by, under Hamming distortion, is given by log of m minus h of d minus d log of m minus 1, as long as d is less than equal to 1 minus 1 by m, and for d greater than that, rate this is given by 0. Now let us characterize this rate distortion function a little bit more. So we know that the rate distortion function is given by this expression. So we are minimizing the mutual information between x and x hat, and remember this minimization is over all conditional distribution q of x hat given x, for which this joint distribution p x times q of x hat given x, this satisfies the expected distortion constraint. So this expected value of this distortion is less than equal to d. Now this is a minimization of a convex function over a convex set for all q of x hat given x greater than equal to 0, satisfying this constraint that sum of q of x hat given x over all x hat, that summation should be 1, and this average distortion constraint should be satisfied. So again I repeat, basically we are minimizing this convex function over this convex set, and we have some additional constraint, which is sum of probabilities is 1, and this expected distortion constraint should be satisfied. So then we can set up our Lagrangian, basically using multiplier method, we can set up our functional. So, this is our objective function, this is the constraint due to this expected distortion constraint, and this is the constraint that comes due to summation of probabilities being equal to 1. Now, let q of x hat be the distribution on x hat induced by this conditional distribution, then this functional can be written like this. If we differentiate this with respect to q of x hat given x and equate it to 0, we get this. So, p of x log of q of x hat given x by q of x hat plus p of x minus summation of p x prime q x hat given x prime into 1 by q x hat into p x plus lambda times p x and this distortion between x and x hat plus mu of x is equal to 0. Now, setting log of mu x to be Vx by Px, from here we get this condition. So, we get Px times log of q of x hat given x by q of x hat plus lambda times distortion measure between x and x hat plus log of mu x, that is 0. Now, this is non-zero. So, what we can get is this is 0. From here we can write q of x hat given x, and that comes out to be this. Now, we do not know lambda, but we know that summation of, this is just a typo, summation of q x hat x is equal to 1. So, mu of x then comes out to be this, and q of x hat given x is this quantity. Next, multiplying both sides by p of x and summing over all x, we get q of x hat is equal to q of x hat into this. Okay. Now, if q of x hat is greater than 0, then what we can write is we get this condition that this summation is equal to 1. So, go back here. So, if this is greater than 0, then you can cancel this out and this will be equal to 1. So, that is what we are writing it here. Now, applying Coulter condition, a partial derivative of j with respect to this q of x hat given x is 0 if q of x given x hat is greater than 0, and this is greater than or equal to 0 if q of x hat given x is 0. Now, substituting this, we get this condition. Now, let us consider a case where we have m independent Gaussian random variables. So, we have m independent Gaussian random variables, and these are denoted by x1, x2, x3, x of m. So, these are 0 mean Gaussian with variance sigma I square. So, they are not identically distributed, but they are independent, and we are considering squared error distortion measure. So, assume that we are given r bits and with these r bits we have to represent this random vector x1, x2, x3, x of m. Now the question that we are asking is how many bits we should be allocating to each of these components. So how many bits should we be allocating to x1, how many bits should we allocate to x2, how many bits should be allocated to xm, such that we minimize the total distortion. So again I repeat, we have m independent Gaussian sources which we are denoting by x1, x2, x3, xm. These are independent but not identically distributed, and we are considering squared error distortion measure. So given there are r bits, the question that we are asking is how many bits should we use to represent x1, x2, x3, x4, xm such that overall distortion is minimized. Now from the definition of rate distortion function, we know that rate distortion function can be written as minimum mutual information between the source sequence x of m and this reproduced signal x hat of m, and this minimization is over conditional distribution such that the expected distortion constraint is satisfied. So now let us look at mutual information between xm and x hat of m. Now from the definition of mutual information, we can write mutual information as differential entropy of x of m minus differential entropy of x of m given x hat of m. Now x1, x2, x3 are independent, right? So we can write the differential entropy h of xm as h of x1 plus h of x2 plus h of x3 up to h of xm. So this term can be written like this. And similarly I can write this h of xm, which is basically x1, x2, x3, xm given xm hat. I can write it in this particular fashion. Now this is conditioned, xi is conditioned on the sequence xi minus 1 and xm. So if we know that conditioning cannot increase entropy. So if I just condition it only on x hat I, then this is a larger quantity. So I can lower bound this mutual information. Now this can be written as summation I equal to 1 to m h of xi minus h of xi given xi hat. Now from the definition of mutual information, this is mutual information between xi and xi hat. So then mutual information between this sequence x of m and x hat of m is lower bounded by mutual information between xi and xi hat sum over I going from 1 to m. And since we know rate distortion function is minimum of this, so this can be lower bounded by r of di, again summation over I going from 1 to m. And we know for the Gaussian source, we know the expression for rate distortion function. If you go back for a Gaussian source, this is given by half log of sigma square by d. So, we can write this as when di is less than sigma I square, else is 0 otherwise. That's why I am just writing this as this operator x plus. Okay. So, this is equal to x when this condition is satisfied, otherwise this is 0. So, then the problem of finding the rate distortion function has been reduced to maximizing half log of sigma I square by di or 0 for I going from 1 to m and minimizing this over di. Summation of di basically is d. Now using Lagrange multiplier, so this is our objective function and this is our constraint, the summation of this di from I 1 to m should be cannot exceed d. So, differentiating with respect to di, we get del j by del di as this, and when we equate it to 0, we get this condition. So, this is interesting. It says that distortion di should be same. Di is equal to some constant lambda dash. In fact, for if xi is Gaussian distributed with 0 mean and variance sigma I square, and if we consider m such independent sources given a square distortion measure, the rate distortion function is given by this expression where di's are equal to some constant lambda as long as lambda is less than sigma I square. Otherwise, if lambda is greater than sigma I square, di is equal to sigma I square, and we choose our lambda in such a way such that sum of this distortion over these m sources, that is equal to d. So, this gives rise to what we call reverse water filling. In case of this parallel Gaussian channel, we saw how we were allocating power. It was like putting water when you have various noise levels. Here it is little different. So, here what we do is we choose a constant lambda and we only describe those random variables which have variance greater than lambda. So, we do not use any bits to describe those random variables whose variance is less than lambda. So, let us just look at, let us say this is x1, x2, x3, x4, and these are the distortions d1, d2, d3, d4. So, we fix our lambda. So, this is my lambda. Okay. So, if, as I said, if lambda is less than sigma I square, di is lambda. So, in this case, lambda is less than sigma 1 square. So, di d1 is lambda. Similarly, d3 is lambda. However, for d2 and d4, lambda is greater than sigma square. So, in this case, distortion will be given by sigma 2 square and sigma 4 square. Okay. And as I said, this is interesting. So we are only going to describe those random variables whose variance is greater than lambda, and no bits are going to be used for those random variables whose variance is less than this threshold lambda. So in the next class, we are going to talk about how we can compute this rate distortion function in an iterative fashion. Now this same algorithm can also be used to compute channel capacity, and that will be the discussion for next class. Thank you.